technology in his day that could get these enormous speeds. But at least he understood the physics of it, and that's what I'm trying to explain here, how an orbit works here. And the real key is to understand that no matter how fast you throw it, all of them will be in the air for 1 second. They will just go a little to a lot further horizontally. So if you throw it really, really fast horizontally, it's going to go really, really far. And then this is the key part in Newton's thinking. That the Earth, let me draw a new picture, is not flat. The Earth is rounded. So if you make a little mound and you put somebody on the top of this mound and you give them something to throw, no matter how fast you throw it, it'll drop 5 meters. And so if you throw it super fast at 8,000 meters per second, it'll still take 1 second to fall that 5 meters. But it'll go horizontally 8,000 meters. Why did I pick 8,000 meters? Because if you were to walk along the Earth for 8,000 meters, because of the curvature of the Earth would dip down exactly 5 meters. So, the object falls 5 meters, and it's still 5 meters above the ground. So it goes again, and it's still 5 meters above the ground. I like to describe it this way. It is falling. It's just moving so fast it misses the Earth. It would look like this. If this is the moon, and here's the Earth, if the moon didn't have a horizontal speed, gravity would pull it in, and it would just hit the Earth. If it had a small horizontal speed, it would move and still hit the Earth. But if you give it a lot of horizontal speed, it will fall and essentially be the same distance from the Earth. It'll miss the Earth. Maybe I'll kind of do this and reset it. It will move and miss the Earth. It will move and miss the Earth. And so Newton explained it in terms of a cannon, because he knew that the speed would have to be really big, and he knew the size and the curvature of the Earth. So he knew that this cannon, for this to work, we would have to throw something, or in this case, shoot something with a cannon at 8,000 meters per second. Nothing was even close to doing that in Newton's day, but at least he could explain it. And so we call this Newton's cannon. I've got a nice little animation here that illustrates Newton's cannon, I think, very well. Let me backtrack here. It's right here. It's called Newton's cannon. And I think it starts right away, so when I click on it, you'll hear the first cannon blast. Here it is. So this is the flat Earth. And it shows a couple of cannonballs, but also showing one that drops. And they always fall 5 meters. It doesn't matter how fast you shoot the cannon. It falls for 1 second. Although, of course, what does matter is it goes further horizontally. So, if we continue with this animation, and we give it some curvature, you will see that now the higher speed has the extra curvature of the Earth. And this one right here seems to get no closer to the Earth. It is that just right 8,000 5,000 meters per second. And I think you see it best on the last part of this animation, where we can see the whole Earth, and it is falling with just the right speed that as it falls closer to the Earth, it doesn't get any closer to the Earth. And so it's always 5 meters away from the Earth. And that's what an orbit is. And so, again, it's a good time to talk about orbits here because we're talking about projectiles, and that's how Newton first understood it. But we're going to expand on this in the next chapter. And so maybe now would be a good time to say, okay, let me close up this chapter and say, okay, there is chapter 4 and all the details of chapter 4. Let's start here, chapter 5. And so as I mentioned at the beginning of today's lecture, this is week 2, and our goal here today is to finish 4, and there we are, finish 4, and to start 5. So let me encourage you to jump into the homework on chapter 4 and keep working on that. I know we still have 6 days away from the test, so no reason to panic yet. But being summer school, this is a pretty quick pace, and you don't want to fall behind on this. And so, like I said with my emails this weekend, if you hadn't done much or anything on the first week of material, which were those 3 lectures and 3 homework assignments and 2 labs, get it done. And so yesterday morning, and it was a holiday when I sent it, but I go, no, look, you just need to spend your holiday. And obviously a lot of you did, because you started asking me questions and emailing back. So I hope everybody did all of week 1, and now you're ready to do week 2. And so that would be today's assignment as you watch this lecture and now do the homework for chapter 4. So let me get started here with chapter 5 and explain what chapter 5 is. And as I said earlier, fortunately 5 and 6 are pretty short chapters. Chapter 6 does get into this, this orbiting stuff here. Oh, I forgot to look at the clock. Ron, can you see the timing on there? How long we've been going here? I want to know when roughly to quit. 4:04. So we've been 44 minutes. Okay, and so we'll go a little half hour, maybe a little bit more, but that'll be a really good jump into chapter 5, so we can wrap it up tomorrow, and then 6, and then have about an hour's worth of time for doing a kind of summary and a review and a test readiness of it. And so let me turn my page here, and right here on the board, chapter 5. And chapter 5, the title of it, and you can see why we're going to get into orbits, is we're going to get into gravity. And so our title is gravity, and gravity does include things like orbits. It does include tides also. We'll talk about that. But the reason it's a shorter chapter than the other ones is a major discovery by Newton. And so Newton comes into play here too. It's called the law of universal gravitation. And it basically says that if you have one object, let me call it object of mass 1, and another object, mass 2, these 2 objects are attracted together by gravity. Here is really an amazing discovery in Newton's time, and why we call it universal is Newton began to realize that the way the Earth is being gravitationally attracted towards the sun, and the way the moon is being gravitationally attracted towards the Earth, and the way an apple would be gravitationally attracted to the Earth, we're all fitting the same pattern. And before Newton, people really didn't know what was going on. The way they explained how the moon was attracted to the Earth, or even not attracted to the Earth, and the way the apple was attracted to the Earth, and the way the Earth was attracted to the sun, and the way the moons of Jupiter were attracted to Jupiter, they had different stories. And so they had like the gravity of Jupiter, and the gravity of Jupiter was different than the gravity of the Earth. And even the gravity of the Earth was different for the apple than for the moon. It was crazy. And there was all these different theories, and Newton noticed that they're all one and the same. That they all behave exactly the same way. And so let me begin chapter 5 by pointing out there's only one law of gravity. And that makes this chapter short and a little bit easier to learn. It also then says that we should call it the universal law of gravity. Because it's true. You could talk about the sun, or you could talk about the whole Milky Way galaxy, or you could talk about other galaxies, or you could talk about something small. And that might be a bit surprise too, is Newton is saying not only are things like the moon and the Earth being attracted to each other, even something that we don't necessarily associate with gravity, like this lead sphere, is then attracted to this lead sphere. And so you can see we're going to have an equation here in a little bit. But I just want to start with the important concept. The universal law of gravity just simply says every object is attracted to every other object. It's kind of a silly notation, but I think it has to be emphasized that even small objects like these lead spheres, even something like this, even this lead sphere and me are attracted. If it helps, I always keep this in mind, that every chair, every student, every person in the world is attracted to me. And I'm being silly here, but it is the same formula that we calculate the attraction between a rock and a car that we would between the Earth and the moon. And as you'll see in the formula, the gravitational attraction between these two objects is really, really small. So we often forget about it. It's even hard then to convince students who are listening to a physics teacher talk about it to say, is there really a gravitational force between those two small objects? And so let me say yes, there is, and yes, it can be measured. And we'll talk about Cavendish in a second and the experiments he did to measure these here. But I just want to start with concept. No equation yet. But just this idea that you pick any two objects. They don't have to be lead. It could be the dirt and the Earth. It could be the rocks in an asteroid. It could even be this nitrogen molecule right here and this oxygen molecule right here. They are still gravitationally attracted to each other, and the way I would calculate them would be exactly the same. And so hence it's the universal law of gravity. And you'll see in a moment when we do the math that the factors that play in are actually the mass of the objects themselves. And so you'll see here as I run some numbers in a second, I will make this statement. I will say that even though these two are attracted to each other, this one is much more attracted to the Earth because the Earth has a bigger mass. Much, much bigger mass. And so when I hold the two, I can feel and even see them drop towards the Earth, pulled towards each other. I don't feel that. Nor do I see it if I drop them together. They just get pulled towards the Earth. And so I think, again, that's why it's kind of hard to convince students that there's not something magical about the Earth that makes gravity It's any object is attracted to any other object. It's just some of these forces, most of the time, are so small we don't recognize them. I do not stand here and feel this tug towards this desk. Oh, pull me over. What I really feel is the largest mass around, which is the Earth. And so I feel this. I feel pulling me down, and I got to use my legs to stand up. And getting pulled over here, I don't really feel. Likewise, there's a desk over here that's pulling me, so I just don't feel those. But I want to convince you, we call this the universal law of gravity because it's any two objects. And again, once I write the formula down here, you'll see that mass plays a big role. That's why another thing I like to say, besides saying, hey, everybody out there is attracted to me, and you know how I can get more attractive? Put on more mass. And so keep eating those cheeseburgers and fries, and the bigger I get, the more attractive I get. And so everybody is more attractive to me. Obviously, I'm being a little silly there. There's a difference between social attraction and gravitational attraction here. But the physical gravitational attraction has to do with the mass. And so now that I think you got the general concept of why we call it the universal law of gravity, and hopefully you're beginning to believe me that it's not just something magical about the planets, it's any two objects, period, end of story. The formula, the mathematical equation that Newton figures out here is this. And so I'll put a little F here and say, okay, so how much force is actually then pulling on object number 2? And Newton, with a lot of brilliant deductive reasoning, realized that it depended on the product of the two masses. That's the first part I was just joking about. That, if I had more mass, it doesn't matter which one, if either one of them have more mass, there's more attraction between those two. It's also why something as big as the Earth would have so much more attraction to me than something like this table, because it's a product of the masses. But another thing to point out, and it would be from center of mass to center of mass, it would depend on how far apart they are. And so he observed that with the planets. He noticed that things like Saturn were much further away than the Earth. And of course, then Mercury was even closer still. And that the distance played a role here. It turned out, as he kind of studied the patterns, that it's the distance squared. Notice I said distance, and I put the symbol R, and we'll continue to do that, but R stands for radius because he was studying the 6 known planets at the time. He was looking at Venus, my very excellent mother just served us nachos and pizza. So was it Mercury, Venus, Earth, Mars, Jupiter, Saturn, and that's all you can see with the naked eye. So those are the 6 he knew of. And as he studied those 6 planets, he began to realize that the force was getting lesser and lesser, if I can use that word, as we moved out further and further. And it wasn't just an inversely proportion, it was inversely proportional to the square of the distance. So that R means distance. It doesn't just mean radius, but remember he was studying the planets, so distance and radius were the same to him. So that's a little confusing. And then he said it's proportional, so there must be some multiplication factor here. And so there is this, what we call the capital G. We call this the universal gravitational constant, right? It's the constant that goes in the universal law of gravity. And that is worth putting a box around, because if I could summarize this chapter, this is how I would summarize it. That right there. That is the only formula and the only thing we are going to discuss, although we're going to incorporate that formula with the past chapters we've been doing. So it's not really that simple of a chapter, but the basic idea is simple. The basic idea is that this is the force between any two objects. You take the mass of the two and their distance, you multiply this by a constant called the gravitational constant, which I haven't given you a number yet. That will tell you how much force is on that object. Now, let me come back to my picture, because if object 1 is putting this much force on object 2, then let's go back to Newton's third law. Then object 2 is putting the same amount of force back on object 1. So this thing about gravity is if 1 puts a force on 2, then 2 puts a force back on 1, and we know they're equal and opposite from Newton's third law. That's our chapter 3. And so this formula is really nice. This formula tells us how much force not only is on object 2, but also how much is on object 1. Now, I must admit, usually we have something like this. Usually we have one bigger object like the Earth, and then we have a second object like the apple, and we want to know what's going on with the apple, and so we want to know the force on the apple, not the force on the Earth. But nonetheless, they are equal and opposite in direction. So keep that in mind, and then of course, once we know the force, we could go back to Newton's second law of motion and divide it by its mass to get its acceleration. So we could do that as well, and we will here. If we don't run out of time here today, we'll do it tomorrow. Now, it was after Newton, quite a bit after Newton, comes this guy named Cavendish, and he's the one who takes Newton's universal law of gravity to what I'll call the useful step. Because Newton had a little trouble here in the sense that he could never find out what this constant was, because as he studied the planets, he didn't know their masses. He knew their distance and he could figure the forces by their motion. He could do another step and only not worry about, say, the mass of the planet, but he still didn't know the mass of the sun, and so he had two unknowns here, and he was never really quite able to figure out what this G was. And so about 200 years later, Cavendish comes along with a really clever experiment, and I will kind of show a model of it. He starts off with this, and he makes a vertical rod, and from this vertical rod he hangs let me get this out of the way. He hangs two masses that are equal, kind of a dumbbell shape, looks like this. And he hangs them from a very strong and thin thread. Now this model is not very thin. This model is designed so you can see it here in a classroom setting. But he hangs it like this. And the first thing he realizes, and let me adjust the vertical height here a little bit, is he realizes that maybe I better give myself a little more room, put it here. That the wind and the shaking really can mess this up. And if there were such things as Nobel Prizes in those days, I'm convinced this would have been a Nobel Prize. He said, well, Newton is saying that these things are attracted to each other. And so he hangs them, and he brings a big weight near this part of the dumbbell, and another big weight near this end of the dumbbell. And in theory, this should be attracted, and so these come together and these come together. And so he tries it the first time and he sees nothing. He goes, well, Newton said they should be attracted. Now they should move not much, because as they move, they are twisting this thread. So that's why it was real important that this thread be very, very, very small and thin, so that it could easily twist. But even then, he couldn't see it much. So this is where he got clever. He said, maybe it is moving so much, or so little, that I can't see it with my eyes, but it's moving enough that if I could just somehow amplify the motion, maybe I could see it. And so on the surface here, I'll represent it with this box, and the surface of the thread, he mounts a little mirror. And he puts himself in a really dark room, and he lets a little bit of sunlight come in and hit the mirror, and it bounces off the mirror and goes to a far wall, like 30 meters away. And if it turns just a little bit, even though you can't see it here, at 30 meters away, he may be able to see the light move on the back wall. And sure enough, he does. And so some other things, which I won't explain in his experiment, allowed him to figure out how stiff the thread is. And between that, he could figure out how much force there is. And so he could come over here to Newton's equation and say, okay, I know the mass of those two objects. They're in my laboratory. I can measure them. And I know how far apart they are. That's easy. And now I finally just figured out an experiment to measure how much force I get from them. And so I can figure out this constant. And so he comes up with the 6.67 times 10 to the negative 11 newtons, meters squared, kilograms squared. Let's talk about the units, but he uses his mass in kilograms and distance in meters and force in newtons. And he comes up with that number, and for the first time in history now, we have something that we can actually use to calculate. We can actually get a number. And so between those two geniuses, Newton and Cavendish, we now have this, where we can calculate the amount of force between two objects using the gravitational constant together with Newton's universal law of gravity. We can find the force between any two objects. And I will point out, and hopefully it is obvious, but is G a big number or a small number? Yeah, it's really, really small, right? 10 to the minus 11 means 0 point, and there would be 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 6, and then the 6, 7. And the reason I want to emphasize it's small is because this explains the concept that I was making earlier, that since this number here is so small, one of these needs to be big. If it's going to be a number that I would say is big enough that I, as a human, with my hands, would even notice. And that's why when I come over here and I grab this sphere, and I will tell you this is 1,500 grams of mass right here. When I hold this in my hand and I say, okay, how much force is between it and the earth, I can feel that with my hand. And in a moment we'll do the numbers, and you will see that the reason I can feel it with my hand is that one of the masses, not this one, but the Earth, is big. But when I try to feel with my hand the force between it and me, I can't feel it. I would need something as delicate as Cavendish's experiment in order to get the force between it and me. And that's because neither this object or the second object, which is me, have much mass. And therefore, once you multiply it by this incredibly small number, the universal gravitational constant, you come out with a force that is so small that it's hard to detect, which is why then it's hard to teach people that every object is attracted to every other object. So that rock over there is attracted to that rock over there. That car is attracted to that car. That car is attracted to that pedestrian. That moth is attracted to that leaf in the tree. The universal law of gravity. Every object is attracted to every other object. But most of these numbers are really, really small. The only ones that really, really count for anything, that really can measure and matter in terms of the motion of the object, are the stuff that's attracted to the Earth, because the Earth has a big mass. And that's why it's easy to think that there's something very special about the Earth, that only Earth has gravity and not the other objects. And that's what I want to keep emphasizing. That's just not true. All right, so let's start a calculation. Let's do two calculations. Let me grab my calculation here. And so now that I hopefully got the main concept of this chapter across here, the universal law of gravity, let's take this lead sphere. Let me just put it kind of at the edge of this table right here. Maybe I'll take this down here now that you kind of saw the model of Cavendish's experiment and how it works. Maybe the first thing I will ask is, if I put this lead sphere and maybe this lead sphere, and I'll just place their centers about 10 centimeters apart. And I ask, how much is this first one attracted to the second one? Let's try a calculation. All right. So using Newton's universal law of gravity, I would start here with this constant. That's this number here. 6.67 times 10 to the negative 11. That would be force in newtons, distance in meters, and mass in kilograms. So there's my G. Then times the mass of object 1 and then object 2. Now, I don't know if you heard me say it just a moment ago, but I said that this object had a mass of 1,500 grams. And this object is basically the same. It has a mass of 1,500 grams also. Okay, so they have the same mass, but watch what happens when I put them into this formula. Do I put 1,500 grams here? Did you see the units I gave you were in kilograms? And so let me give you a little warning here. Newton's and Cavendish's, well, the universal gravitational constant discovered by Cavendish and the universal law here are written so that the masses need to be in kilograms. So I deliberately gave it to you in grams because that's not how I'm going to put it in the formula. So I'm going to change 1,500 grams to kilograms, and that comes out to be 1.5 kilograms. So that's the mass of the first lead sphere. The second one has the same mass, 1.5 kilograms. And I also mentioned how far apart are they. And I said, and I just roughly put them here and said, okay, let's call that 10 centimeters. But again, I deliberately said centimeters because, let me come back here. What are the units of this universal gravitational constant? They are in distances of meters. And so if I were to give it in centimeters, which I did, that's fine, but that's not what goes into that formula. That formula is looking for things in meters. And so 10 centimeters is a tenth of a meter. So you will probably need to go back to chapter 1 many times in this chapter and make sure that you convert your units. You convert all your distances to meters and all your masses into kilograms. That's how this one is set up. All right. Then other than that, I can get out my calculator. And so I'll do the numbers first. So let me grab my calculator here. And my calculator then says 6.67 times 10 to the negative 11. Okay, good. Times the first mass, 1.5, good. Times the other mass, 1.5, good. Divided by 0.1 squared, and then I'll hit enter. And so this comes out to be 1.50 times 10 to the negative 8. Now if we look at our units, right here, meters squared would cancel with meters squared, good. Kilogram times kilogram would be kilogram squared, and it would cancel with kilogram squared, and you'd be left with newtons. And so that's our first calculation, and that's really what this first half of the chapter is, and we're getting close to our quitting time here. I want to do one more calculation. We'll call it quits for today. But notice, I'll say it again, the universal law of gravity is really what this chapter is all about. And it doesn't matter what objects I have, I'm going to calculate them exactly the same way. I need to have my mass in kilograms and I need to have my distance in meters, but other than that, I'll just put them into this formula. And so when the units cancel off, I will get newtons. I will pause for a second before I do this second calculation and say, is that a big number or a small number? Yeah, and 10 to the minus 8 is a really, really small number, which is why, as I was saying earlier, the attraction between these two is so small, it's really hard to convince you that there's a gravitational force between them. That's why it would really take Cavendish and his brilliance and his really meticulous detail on measuring things accurately and carefully in order to figure out what this number is. Because the second calculation I want to do is, let's just get rid of the second sphere and just ask again, this first sphere is also attracted to the Earth.